This lecture, entitled Science is a Way of Viewing the World, covers all of section 1.2 in the book. This includes the subtopics of the scientific method, the language of science, and scientific revolutions. The main learning goals of this learning module are to be able to describe the scientific method. If you find the material in this module is too basic, then it can be skipped. As an introductory science course, it is necessary to present foundational material. Many students have recently taken science classes in high school and thus may find this lecture too elementary. The chapter title is Thinking Like an Astronomer. Niels Bohr is quoted as saying, "A physicist is just an atom's way of looking at itself. Astronomers think like that." The scientific method is a systematic way of testing new ideas or explanations. This lecture explains how the scientific method works and how it differs from other philosophies. Science uses math. Science uses a whole lot of math. Formulas are derived from other formulas. Math is founded on axioms. An axiom is a proposition that is assumed to be true without proof for the sake of studying the consequences that follow from it. A mathematical theorem is a logical consequence of axioms. For example, here are the field axioms of algebra. And here are the axioms of geometry. Remember learning that a straight line segment can be drawn between any 2 points? These are the geometry rules you learned in school. You learned the rules, and then you learned how to prove things using the rules. Mathematicians prove things. The basic structure of a proof is a series of statements, each one being either an assumption or a conclusion that clearly and logically follows from an assumption or a previously proven result. As an example, consider Pythagorean theorem. A right triangle has a 90-degree angle like the orange triangle here. The Pythagorean theorem states that the sum of the square of two sides lengths of a right triangle equals the square of the hypotenuse. Here is an example of a mathematical proof. Use the algebraic relationship of the quantity a plus b squared. Rearranging the shapes, we see that the sum of the squared a squared and b squared has to be equal to c squared. In math, knowledge is that which can be logically proven. A great debate is taking place among mathematicians and philosophers as to whether math was discovered or invented. Is math the native language of the universe itself, existing whether we find it or not? Or did man create math to understand the universe better? Math itself can't answer that question. Epistemology is the branch of philosophy that studies the theory of knowledge, of how we know something to be true. Epistemology studies the nature of knowledge, the rationality of belief and justification. According to Wiki, much of the debate in epistemology centers on 4 areas. 1. The philosophical analysis of the nature of knowledge and how it relates to such concepts as truth, belief, and justification. 2. Various problems of skepticism. 3. The sources and scope of knowledge and justified belief. And 4. The criteria for knowledge and justification. Epistemology is the investigation of what distinguishes belief from opinion. It is not a mathematician's opinion that the Pythagorean theorem is true. It is a belief that it is true. The justification for mathematics beliefs come from the proof based upon axioms. Not all knowledge can be proven from axioms. Here are a few examples of epistemologies. Empiricism emphasizes the role of experience and perception. It requires experiment as a basis of knowledge. Idealism is the belief that knowledge is primarily innate and requires intuition as a relevant theoretical process. Rationalism is the view that regards reason as the chief source and test of knowledge, or the criterion of truth is not sensory but intellectual and deductive. On the other hand, constructivism is the view that knowledge is a construct of man and not the neutral discoverer of some object or external truth. Science requires experimental evidence for knowledge to be accepted. There are 2 related central concepts for experiments. The first is testability. Any statement in science has to be testable. There has to be some real hope of deciding whether or not something is true or false based on real experience. The second concept is falsifiability. It has to be possible to conceive of an observation or put forth an argument which proves the statement in question to be false. Karl Popper proposed an epistemological methodology for evaluating hypotheses, including those that could not be experimentally tested, and insisted that the term scientific can only be applied to statements that are falsifiable. He asserted that no empirical hypothesis, proposition, or theory can be considered scientific if it does not admit the possibility of a contrary case. If I said the moon is made of green cheese, that is a falsifiable statement. We can go to the moon, collect samples, evaluate them in the laboratory, and prove that they are not made of green cheese. Here are some statements that are not falsifiable. A tautology is unfalsifiable. Black is black. You can't argue with that. A claim that contains an internal contradiction can't be falsified. A claim that is used to predict everything is not falsifiable. And claims that do not make predictions at all are not falsifiable. While math has its axioms, science has its scientific principles. These are assumptions that science takes to be self-evident. The first is the principle of natural causality. Events result from natural forces, and evidence from nature has not been deliberately distorted. The second is the principle of similar perceptions. Any other researcher will perceive the same events and make the same observations. So it is logical to accept the observations of others as reliable. If we didn't assume that researchers have similar perception, how could we determine if experiments were repeatable? Finally, the cosmological principle, which is the foundation of astronomy, states that on large scales, space and time are uniform, and that the laws of physics apply everywhere in the universe. The cosmological principle is the central concept of astronomy. This testable assumption states that the laws of physics that apply here and now have applied everywhere in the universe at all times. There is nothing special about our time or place in the universe. The cosmological principle means that our view from Earth is not special or unique. On a large scale, the universe is the same everywhere. Matter and energy obey the same physical laws everywhere, and we can learn about distant objects by studying nearby ones. In science, there is a hierarchy of credence, that is, our belief or acceptance of something that is true. If something can be falsified, that is, some experiment or argument could be given that would show the statement to be false, it is a scientific statement. A hypothesis is a falsifiable statement that explains a phenomenon. A theory is a hypothesis that some tests have failed to disprove. A physical law is a theory that is well established and of fundamental importance. None of these concepts involve proof. Mathematicians prove their knowledge. Scientific theories are eternally subject to test and revision. Albert Einstein is quoted as having said, "Many experiments may prove me right, but it takes only one to prove me wrong." The book offers us this diagram of the scientific method. You start with an idea, create a hypothesis, make a prediction, and test the prediction. If the test supports the hypothesis, then you make more predictions and continue testing. If the test does not support the hypothesis, then you have to revise your hypothesis. Remember back in the days when you learned basic physics about all those simple machines? Science classes were taught as encyclopedic knowledge. Everyone learned the same things. Then you learned how to do research independently. You evaluated some system, breaking it into its component parts, and then you started doing science fair projects. For the typical K-12 science fair project, you select a topic, research that topic, define the components of the system, event, write timelines, equipment, find analogies. You figure out what the central question is that you want to answer. Then you create a hypothesis. Then you design an investigation. Then you make a prediction along with an experiment that you can potentially show your hypothesis to be false. You write a list of what you need to do and what you plan to do. You conduct your investigation, keep a logbook of experiments, data gathering, procedure modification, organize, analyze, graph, visualize, and interpret data, and then you draw conclusions. The scientific method at face value isn't very different from a science fair project. You start with an idea, and eventually you keep testing it to find out if it's true or not. You revise it when it's false, and you keep testing it to show that you can gain confidence in your idea. Science is full of surprises, though. You can get unexpected results, and sometimes the investigation undertaken is purely one of exploration. Researchers are subject to peer review. Pearson uses this graphic in their books, they being the process of observation leading to theory. The eternal cycle of theory, prediction, observation efficiently captures what science is all about. The idea is that no theory is completely correct, but if it has not been falsified, it can be accepted as truth. Science truth is different from mathematical truth, which must be proven. Occasionally, there are more than one theory that make the same predictions with equal accuracy of experimental results. Occam's razor can be used as a tiebreaker. Occam's razor says that among competing hypotheses, the one with the fewest assumptions should be selected. It is a heuristic maximum and not a logical reasoning strictly. In my own experience, the scientific method is a cycle like this figure, which separates reality in the green boxes on the left from our abstraction of reality, the mathematical modeling of our theories, in the blue boxes on the right. Inductive reasoning, based on data analysis of some observations, results in mathematical models. These models are implemented in some simulation system to generate predictions about the real world. The simulation results are interpreted and used to plan an experiment through deductive reasoning. The experiment is conducted and data taken during the experiment is exaggerated. Collectively, experimental data form an observation of reality, and the process begins again. Another way of looking at it is that aggregation of our measurements and observations is our knowledge. It is our reality, whereas our ability to predict and explain that knowledge is our understanding. Modeling is primarily an inductive process, and making predictions is primarily a deductive process. A big part of science is to classify things. A taxonomy is created by evaluating similarities and differences of entities that have been observed. This graphic, for example, shows the classification of numbers. And this graphic shows the classification of malware. This graphic shows the classification of rocks. There are three main groups: sedimentary, igneous, and metamorphic. The way we find things out often involves a collection of things. Once we have a collection started, we characterize the entities in that collection. We use their characteristics to form a classification system. We could conduct a survey and use our new taxonomy to discriminate and classify new members of our collection. Our taxonomy might change. We might pick a few members of that collection to do a case study. We create a timeline, look for trends and correlations to understand that one member of our collection in great detail. We think if we understand that one member, then we can extrapolate and we will understand all the others that are similar to it. We step back and solve problems we know how to solve by making analogies and approximating, but always we are testing our hypotheses. Statements about facts about the physical universe must be supported by physical evidence. To contrast Sagan's wisdom with the unnecessary violent controversies that take place in society, I want to read this quote from Isaac Asimov to you verbatim. It might come in handy one day when you're trying to reason with someone. This is the quote. There is a cult of ignorance in the United States, and there always has been. The strain of anti-intellectualism has been a constant thread winding its way through our political and cultural life, nurtured by the false notion that democracy means my ignorance is just as good as your knowledge. Science is greatly abused in popular press, social media, and politics. There seems to be a notion that democracy means everyone's belief should be given equal regard, and that consensus or majority of opinions may be regarded as truth. To impose their will, a lot of logical fallacies are hurled, cherry-picked facts, confirmation bias, false dichotomies, and post hoc ergo propter hoc fallacies are among the most frequent. When that doesn't work, obfuscation and name-calling follow. Ultimately, it ends with appeals to authority. If those types of logical fallacies are unfamiliar to you, please take the time to go through some of the material in the Logical Fallacies folder and do the Logical Fallacies Exploration Lab as one of your labs. Scientific theories must be testable and falsifiable. All scientific knowledge is conditional and provisional. Our understanding can change due to additional experimental findings. This is how science makes progress. Richard Feynman cautions us that the easiest person to fool is yourself. In summary, science has to agree with nature. Existing, accepted ideas are subject to challenge via the scientific method. All theories must ultimately agree with nature. And I'll close this video with a few quotes from famous scientists. Richard Feynman famously said, "I would rather have questions that can't be answered than answers that can't be questioned." And Stephen Hawking said, "Intelligence is the ability to adapt to change." This next set of slides introduces the topic of scientific revolutions. The idea of scientific revolutions dates back to Thomas Kuhn. Kuhn thought that progress in science happens through revolutions. Most of the time, researchers would find that experiments fit theory. During these normal periods, most scientists are bricklayers, filling in voids and giving further credence to existing theories. And not many people are questioning the paradigms of science. Eventually, data doesn't fit theory. During periods of scientific crisis, violent arguments erupt between proponents of new and old ideas. Eventually, the revolution takes hold, and scientists reject the prevailing ideas and support a new way of viewing the world. This graphic shows the scientific revolution we know of from Copernicus putting the sun at the center of the solar system. It took many years further for it to be accepted and for Newton to put forth his laws of motion and universal law of gravity to explain what Copernicus originally proposed. There are many famous experiments of biology and chemistry that lead to scientific revolutions. A couple of key experiments important to physics led to our current understanding of quantum mechanics. These include the photoelectric effect, the shape of the black body curve, and Young's double slit experiment. We'll talk about them more in the learning modules about light. For now, just understand the need for and acceptance of quantum mechanics arose from experiments that were not explained by classical physics. This leads us to have what on macroscopic scales seems like bizarre points of view, that light can have both behaviors of a particle and behaviors of a wave. Sometimes science has a crisis that is data-driven. Observations of the Kuiper Belt found that Pluto had companions. Looking at the new data, astronomers realized that the definitions of planets needed to be modified. This eventually led to the reclassification of Pluto as a dwarf planet. Science is self-correcting eventually, even when strong emotions are involved, said Mike Brown, who had a huge role in redefining Pluto as a dwarf planet and wrote this highly recommended book, How I Killed Pluto and Why It Had It Coming. In summary, scientific revolutions arise from realizing the current theories are incomplete or incompatible with data.